So now let's talk about something that we might find interesting, which is the inverse trigonometric functions. We want to find the derivative of the arcsine of x. Now recall, if we have an inverse function that we want to find its inverse, f inverse prime of x is going to be equal to 1 divided by f prime of f inverse of x. So let's see where that leads right here. Let's say that we're going to start with the idea that our inverse function f negative 1 f inverse of x is already arcsine of x. Recall something about arcsine of x? Well, let's make sure that you do. Whenever we choose values of x for this function, they have to be between negative 1 and 1. And the the range will give us values somewhere between negative pi over 2 and positive pi over 2. Now, if we keep those things in mind, then let's figure out what was f of x. Well, f of x, remember the original function, is sine of x. Right? That's the definition of an inverse trigonometric function, inverse sine of x. So if this was our domain and range of our inverse function right here, then we must make sure that we're talking about f of x being the kind of function whose domain is negative pi over 2 to positive pi over 2. And whose range is negative 1 to 1. Right? Because a function and its inverse domain and range switch. All right. So keeping that in mind, what could we say? Well, by this formula, we know that f prime of x is going to be cosine of x. And so if we use our formula right here, we could say, well, that's easy enough then. F inverse prime of x right here, our derivative of our cosine should be the cosine of the arcsine of x. We figure, oh, well, that's nice. Well, that means we're done, right? Well, no, because that's a little bit of a complicated function. We actually have ways of simplifying that. We might note, for example, that if we were to pick an angle whose arcsine gave us x, there would be an angle, theta, with a ratio of opposite to hypotenuse of x over 1, which would mean that we would have an adjacent side of 1 minus x squared using our Pythagorean theorem. And of course, the cosine of that angle is our value, right? So we're taking 1 over the cosine of some angle whose arcsine is x, which means 1 over the square root of 1 minus x squared. And we can see, by the way, that if we were to actually work this out, then we're saying that the derivative with respect to x of the arcsine of x won't have any trig function in it at all. It will be a ratio, 1 over the square root of 1 minus x squared. Interesting. Now, is there any other independent verification of this thing? Well, yes, there is. As a matter of fact, we could use a little implicit differentiation to verify this formula too, right? Let's say that I told you that y was equal to the arcsine of x. What else could we say? Well, that would mean that the sine, not cosine because I'm getting a little ahead of myself again, the cosine of y would equal x. And by implicit differentiation, we take the derivative with respect to x on both sides. So we take the derivative with respect to x of the cosine of y and set it equal to the derivative with respect to x of the function x. What happens? Well, I'm going with cosine, and that's a mistake again because I'm just having too much fun today, getting ahead of myself. Sine of y here. So we're still taking the sine of y because it was an arcsine. And we take its derivative. And our derivative is cosine of y, there we go, times the derivative of y. That would equal 1. What do we discover? Well, y prime is equal to 1 over the cosine of y. And not only that, y prime is equal to 1 over the cosine of the arcsine of x, which was y in the first place, remember? And if we make the appropriate substitution, as we did right here in this middle portion, guess what? Y prime is indeed 1 over the square root of 1 minus x squared. How useful is that?